Okay, imagine that you have a uniform rod of length L and mass M, mass equals mass, and it is free to rotate about a pivot point fixed at one end. So the rod is horizontal. I'm going to let go, and it's going to rotate fixed at that one end. The question is, where can you place a penny along this rod such that as it falls, the penny does not lose contact with the rod until it slides off. So until the rod is at a location where the penny would continue straight down. Okay, so it's not going to stick to the thing, but as soon as the rod is at the point where the penny can slide off of it, then it would in fact fall off. Okay, so at what length is the acceleration, at what location is the acceleration, the tangential acceleration of the rod, the same as the acceleration of the penny? Okay, well, we need to understand what the tangential acceleration of the rod is in general. So let's imagine what will be the acceleration, what will be the rotational acceleration. From that rotational acceleration, we can find the tangential acceleration. So let's imagine if we're going to look at the change in rotation of this rod. It is stationary, it's going to change its rotation. We know that to get something to change its rotation, we apply a net torque. We know that that net torque is going to equal the moment of inertia times the angular acceleration. So what's the net torque acting on this rod to know what that acceleration is at the beginning? Well, to find the net torque, we want to draw an extended free body diagram of the rod. So here's the rod. We'll draw the forces acting on that rod. So we know that there's a force of gravity. It's between the rod and the earth, and it is acting at the geometric center if this is uniformly distributed. And we know that force of gravity equals mg, or the mass of the rod times gravity. Now it's being held in place by a pin, and we typically will just represent that pin as having both a horizontal and a vertical component. Now, it may not have those components, and in this case we might see that it doesn't, but I always like to just put them in, and then if I solve for those components and find 1, 0, so be it, or it's in the other direction, so be it, okay? So what is the net torque acting on this rod about that pivot point? Well, if we set our pivot point to be there, both of these forces, well, they don't exert a torque. They're at the pivot point. So it's only the force of gravity that's exerting a torque on the rod. So our radius is from the pivot point to the force. So there's the radius. And we extend that radius and curl, and there is our angle. Now I'm just going to look at the magnitude of that torque. The direction is going to be in the clockwise direction, so negative. But we're just going to look at the magnitude at this time. Well, we know the force of gravity is mg. The radius of length L is L over 2. And the sine of 90 is 1. So we see that the net torque acting on this rod is mg L over 2. And that has to equal I times the acceleration, the angular acceleration. Well, we can look up the value of I, or the relationship for the moment of inertia of a rod rotating about one end. We know that the moment of inertia of a rod at the end is equal to 1/3 the mass times the length squared. So 1/3 m. I'm just going to double check that. Yep, m times the length squared. So putting that into our relationship, we have mg times the length over 2 is equal to 1/3 m length squared times our angular acceleration. So doing a little equation cancellation, my m's cancel, one of my l's cancel, and I find that I bring the 3 over. I have 3g over 2l is equal to my angular acceleration. So the angular acceleration is dependent on the length of the rod, and it's equal to 3g over 2l. All right, so if that is the case, what is the tangential acceleration at the end? So what's the tangential acceleration at that point? Well, we know that the tangential acceleration is equal to the angular acceleration times the radius. Let's say I have a meter-long bar, okay? So if we'll put in some values here. If my length, if I have a meter stick, then my angular acceleration is equal to 3g over 2 times 1 meter times the radius of 1 meter, because I'm at the end. My tangential acceleration is 3g over 2. That's greater than gravity. That tells us that at the end, the acceleration of that particle at the end, the acceleration of the mass at the end of this rod is bigger than g. So if I were to put a penny on the edge of this meter stick and let it freely fall, that penny would fall slower, accelerate slower than the rod. All right, so try that if you don't believe me. But that's what happens. When I put a penny on the rod and let go of the rod will fall and the penny will fall separately and later. So where can we put the penny so that it falls with the rod? Where can we put the penny so that the acceleration of the penny is the same as the acceleration of the rod? And more specifically, the tangential acceleration. Well, we know for a meter stick that we know for any length, right, that angular acceleration for any length rod is 3g over 2 times L, right? So we know that the angular acceleration is 3g over 2L. All right. If we want the tangential acceleration, which is alpha times r, to equal g, then my marker went bad. What is r? So we need 3g over 2L is equal to, that's alpha, whoops, times r is equal to g. So solving for r, we get r is equal to 2L over 3. So if I put my penny at 2/3 the length, the tangential acceleration at that point is equal to the acceleration due to gravity. And the penny will begin to fall at the same rate as the rod and not separate until the rod is below the penny, until it falls off the rod. All right, so recognizing what forces are acting, finding the net torque, which is going to give us the angular acceleration, using the known values of the moment of inertia, or the rotational momentum, the rotational moment, and then solving for what we need. All right, good job.